In the stillness of the cosmos, the universe behaves like a vast cathedral of LateScienceUniverse, silent and immeasurably precise. For billions of years it has followed the same sacred script. Light races forward at its immutable speed, carving straight lines through the darkness. Gravity folds space into elegant curves, shaping galaxies like a sculptor working in slow motion. And time, that quiet river, flows in a single, unwavering direction, patient, obedient, unbroken, for generations. Humanity believed these laws were the foundation of everything that exists, immutable, eternal, perfect, until something appeared. Something so delicate and yet so violently out of place that it carved a thin fracture through the floor of our understanding. It began not as a roar, but as a whisper, a faint measurement, a strange signal. A particle behaving with the elegance of disobedience. It did not explode into existence. It merely slid across the rules, like a shadow cast from somewhere reality had not accounted for. It did not break the laws of nature. It simply acted as if it came from a different version of them. Around the world, physicists stared at their data, blinking in disbelief. Instruments built to measure the familiar began reporting the impossible. Clocks disagreed with themselves. Patterns formed where randomness should reign. In the universe, for the first time, looked back at the scientists who had spent centuries deciphering it. This was not a glitch, not an error. Something had arrived, something that should not exist. And if the universe can do this, then the universe is not what we think it is. The opening closes on a cold, unblinking truth. The universe never promised to be understandable. It only promised to exist. In a remote valley of the western United States, where mountains rise like silent sentinels guarding the sky, a laboratory stands half-buried beneath the soil. Most of the world knows it only by a name: LaGo, the Laser Interferometer Gravitational Wave Observatory. A structure of steel, mirrors, and impossible precision, built to detect the faint trembling of space-time itself. It was designed to listen to the universe the way a conch shell listens to the sea, not through loudness, but through the trembling echo of distant catastrophized black hole collisions, neutron-star mergers, the soft rumble of gravity stretching space. On a quiet morning, under pale gray clouds, the detectors hummed with the monotony of routine. Their lasers glided along 4-kilometer vacuum arms, reflecting between mirrors polished smoother than any surface on Earth. The system waited for the universe to speak. But what it registered that day was not a ripple in space-time. It was something far stranger. The scientists on duty were not expecting anything unusual. They were running a calibration sequence routine, tests meant to map out sensitivity, clear out noise, and prepare for the next observation cycle. During calibration, the detectors were not supposed to capture meaningful data. They were simply being tuned like a violin before a performance. Yet, in the middle of this quiet tuning, a pulse appeared. A single, sharp, clean oscillation. Too clean, too symmetrical. The kind of signal no gravitational wave ever produces. It arrived with perfect mathematical order. It's like a note in a song that had been carefully composed rather than forged in the chaos of colliding stars. At first, the on-site physicists assumed it was an instrumentation hiccup, thermal noise, ground vibration, or one of the thousands of mundane disturbances sensitive detectors can pick up. But when they checked the logs, a question rose like a cold shadow. Why had the pulse been recorded 3 milliseconds before the detector officially switched on? The calibration signal was not active. The instruments were in a pre-measurement state. Nothing should have been detectable at all. The lasers were active, but the system that translates their interference into data hadn't yet begun its sequence. And yet, a pulse had arrived. A pulse with no physical pathway. A pulse without causal origin. It was as if the detector had listened to a sound before its ears had opened at the control desk. Dr. Mara Ellison stared at the screen in disbelief. She had spent 15 years studying gravitational wave signatures, beginning her academic life under mentors who had worked directly with Kip Thorne. She knew the language of space-time ripples by heart, their shapes, their harmonics, their messy asymmetries born from violent, astrophysical events. What she saw now was not that language. It was something else. Something written with a precision nature rarely uses. Her first instinct was the instinct of every scientist. Find the error. She reopened the logs, checked the photodiode readings, reviewed the vacuum stacking, inspected the control photons, and even rechecked the synchronization with the atomic clock systems. Everything appeared normal, except the one thing that was not. The signal existed. She zoomed into the waveform. Its symmetry tightened into an elegant curve. Like the mathematical lattice of a quantum harmonic oscillator, far too perfect to emerge from an astrophysical source. It was as if the universe had spoken, not in a roar, but in a single, carefully carved whisper. Ellison called in another researcher, then another. Soon, the control room filled with quiet voices, hushed, not from excitement, but from an unspoken fear. They ran simulations to see if it could be internal noise. But the simulations disagreed with reality then. Something more unsettling was noticed by a postdoctoral researcher named Rafael Soto, who sat at a corner terminal comparing timing logs. The pulse is earlier than the control initialization, he murmured. Barely above a whisper, Ellison looked up. Earlier, yes, Soto said, tapping the time stump. It's recorded before the measurement cycle, before the sequence even begins. She leaned in. He was correct. The detector had captured something that arrived before the system was active, before it was capable of registering anything, before the universe had given it permission. For a long moment, nobody spoke. The silence held the weight of unformulated questions. Could time-stamping be misaligned? Could the atomic clock have drifted? Could the FPGA board have misfired? Each possibility was examined and dismissed one by one. Finally, Ellison spoke the thought everyone had been avoiding. It looks like a pre-causal event. The room froze. Physics has many allowances, but causality is not one of them. By that afternoon, the data had been sent to Liga's secondary site in Hanford and then to Liga Virgo collaborators in Europe. The early responses were identical. Preliminary shock. Followed by the ritual skepticism of deeply trained scientists. Check your clocks. Reanalyze environmental noise. Run a diagnostic dump. Could it be cosmic rays? Maybe a glitch in the ADC. Normal explanations. Comfortable explanations. But comfort evaporated when the Virgo Observatory in Italy checked its own logs. During the exact same global timestamp, a weaker, eerily similar signature had been recorded. Not as clean, not as defined, but undeniably present. And like the American detector, the Italian system had captured the pulse before its initiation sequence. Two detectors, separated by continents. Both hearing a whisper before they had begun to listen. This was no instrumentation accident. It was something deeper. Something that seemed to exist outside the sequence of cause and effect. To rule out coincidence, the team turned to a third system, the Kamioka Observatory's Super Kamiokande neutrino detector in Japan. Unlike LIGO, Super K detects subatomic neutrinos using vast tanks of purified water and photomultiplier tubes that capture blue Cherenkov. Light the radiation produced when neutrinos pass through water faster than light does in that medium. Its sensitivity is not two gravitational waves, but to the universe's most elusive particles. Yet remarkably, the timestamp logs in Japan hinted at a faint burst of unexplained photonic activity. Also slightly preceding its scheduled detection cycle, it was weak, barely above threshold. But it was there. 3 different observatories, 3 different instruments, 3 different detection methods, all catching shadows of something that should not exist. Word traveled quietly at first. Shared only among a few teams through encrypted channels and private Slack workspaces. Nobody dared to publish it. Nobody wanted to become the scientist who cried new physics over a system glitch. Modern researchers carry the weight of decades of scrutiny. Extraordinary claims require evidence that withstands the merciless pressure of global replication. For days, the LIGO team prepared to repeat the calibration sequence, this time under tighter conditions. They isolated the detector from environmental noise, shut down auxiliary electronics, synchronized clocks with GPS and hydrogen maser atomic standards, and recalibrated laser phase shifts down to picometer tolerances. Then they reactivated the sequence again. The pulse appeared again, slightly before the detector initialized. Again, with impossible precision. By now, the team was no longer dismissive. The anomaly had replicated under controlled conditions, and it was not alone. A precursory signal appearing without causal origin. A waveform too mathematically perfect to arise from natural astrophysical events. Instances appearing across multiple international observatories. Scientific community had encountered unexpected results before cold fusion claims. Superluminal neutrinos from OPRA miscalibrated equipment that mimicked new physics. But nothing in the past century had displayed this level of consistency across unrelated instruments. Late one evening, as the research teams expanded their analysis, a new detail emerged, one that tightened the mystery further. When comparing timestamps across LIGO, Virgo, and Super Cameo Condi, researchers found that the anomalies were not identical. Each appeared slightly out of phase, not by seconds or milliseconds, but by fractions of Planck time, the smallest meaningful unit of time in theoretical physics. The universe, it seemed, was whispering not in one voice, but in three overlapping harmonics, each out of sync in a pattern that defied easy interpretation. Some theoretical physicists suggested that if the anomaly were real, if it were truly pre-causal, then these harmonic offsets might represent interference patterns, not from gravitational waves or neutrinos, but from a deeper substrate of reality, a substrate beneath spacetime, a layer where time does not flow forward but exists in a kind of superposition, flickering between states the way quantum particles flicker between probabilities. As Dr. Ellison reviewed the data in her office, the glow of her monitors reflecting in her glasses, she saw something else, a pattern hidden in the harmonic offsets. A symmetry that resembled structures predicted by certain quantum gravity models, specifically those involving loop quantized geometries and causal set theory. These theories suggest spacetime is not smooth, but granular, composed of discrete chunks bound by mathematical relationships. If true, then the anomaly might not be breaking physics. It might simply be interacting with physics on a level humans rarely glimpse. The possibility was terrifying. An exhilarating and emergency virtual meeting was called among partner institutions. Over 200 researchers joined the encrypted feed. Screens flickered with faces from California, Pisa, Tokyo, Paris, Munich, Beijing, and Sydney. Nobody used casual tones. Every voice carried the weight of scientific history. Teams presented their findings. Arguments erupted over interpretations. Some suggested an unprecedented form of quantum noise. Others believed it might be evidence of a non-local phenomena, a violation of locality itself. A few theorists proposed something even stranger. The signal could originate from a region of spacetime, not bound by classical temporal order, a place where time is not a river, but a field. The debate stretched into the early hours of the morning. Eventually, the group reached a single consensus: replication was essential. Not once, not twice, but across multiple detectors under varied global conditions. In the following weeks, laboratories around the world, from CERN to the IceCube Neutrino Observatory in Antarctica, joined the effort. IceCube, buried deep beneath the South Pole's ice sheets, detects neutrinos passing through Earth using photodetectors submerged in the frozen darkness. Its environment is insulated from ground noise, atmospheric interference, and electromagnetic contamination. If IceCube detected anything resembling the anomaly, the implications would be profound. And so, on a cold night beneath the southern lights, the detectors listened. A faint burst, barely distinguishable, just above background noise, but present. The anomaly had spoken again. Even beneath the ice, by now, the scientific world understood. This was no mistake. No glitch. No easily explained quirk of machinery. Something had emerged, a phenomenon arriving before the universe permitted cause. effect or measurement, something that treated the rules of reality not as laws, but as suggestions, and across every observatory, every detector, every research group, one question echoed: if this signal is real, what does it say about the nature of reality itself? The chapter closes as global institutions begin coordinated experiments, synchronized across time zones, tuned to nanosecond precision, a worldwide effort to replicate the impossible, to measure the unmeasurable, to confront the first hint that the universe may not be obeying its own rules. The first days after the anomalies' confirmation unfolded like a quiet storm, disturbance spreading invisibly through the scientific world, shaking foundations that had seemed unshakable. In universities and observatories across the globe, screens glowed through the night as researchers stared at numbers that refused to obey the most sacred principles of physics. It was not simply that the anomaly was unexpected, it was that it was impossible. Every rule that governed the universe seemed to stand in opposition to it, as if the event existed not within the universe but alongside it, following laws that were familiar only in outline and foreign in meaning. The signals, those thin, quiet pulses that had arrived before detectors had opened their metaphorical eyes, were the first known measurements not bound by causal order. They appeared in instruments before the instruments were active. They registered in systems before the systems initiated. They were sequences without cause, effects without events, signatures without origins. The universe had permitted an outcome with no preceding action. To physics, this was not merely unusual. It was catastrophic. Einstein's general relativity held SpaceTime as a smooth stage on which matter and energy performed according to definite rules. Causal order event, a preceding event B, was as sacred a principle as mass or motion. But this anomaly, with its pre-causal timing, seemed to slip outside relativity itself, mocking its boundaries with a kind of serene indifference. Models were built, equations were rearranged, tensor fields were reinterpreted. None could accommodate a signal that arrived before the measurement, sequence that should have made it observable. Across the community, a phrase began quietly, circulating, a phrase whispered half in awe, half in dread: "This one breaks time." In theoretical circles, the reaction was more philosophical, yet no less shaken. If an event appears before the conditions allowing its appearance, what meaning does cause retain? What does it mean to measure something that should not exist? And how can the universe produce a phenomenon that denies the fundamental logic on which physics is built? Had Stephen Hawking still been alive? Many suspected he would have called it what several younger researchers reluctantly began to voice: a rupture in predictability. A tear not in space-time itself, but in the rules that allow space-time to make sense. Hawking had explored singularities, paradoxes, Hawking radiation, the information problem concepts that stretch intuition to its limit, yet even those extreme ideas remained coherent within the tapestry of causality. This anomaly did not stretch the tapestry. It pierced it in meeting rooms, on encrypted video calls, and across collaborative documents filled with spectrograms and timing logs. Disbelief became a central part of the scientific conversation. Some claimed the anomaly was a measurement error, perhaps a new form of electronic echo, or a flaw in clock synchronization. But atomic clocks are humanity's most precise instruments. They drift only a billionth of a second over centuries. Quantum timing systems are even more stable, and the anomaly had appeared across multiple observatories, across continents, across radically different detection mechanisms. It behaved like a universal event, not a local glitch. The analysis deepened. LIGO's supercomputers were tasked with simulating the conditions under which such a pre-causal pulse might appear. Hundreds of processors worked in parallel, reconstructing scenarios from quantum vacuum fluctuations to hypothetical higher-dimensional reflections. Each simulation crumbled beneath the same contradiction. Any event that appears before the system that records it violates relativity's causal structure. Nothing travels faster than light. Nothing outruns the causal fabric of space-time, and yet something had. The supercomputers did not merely fail to explain the anomaly, they confirmed it. Every recalculation sharpened the impossibility. Every attempt to reinterpret the data ended at the same conclusion. The signal's temporal ordering contradicted the mathematical structure of the universe. Review boards convened. Panels of senior physicists, some in their 70s, veterans of particle physics and cosmology, reviewed the logs with the cautious skepticism earned through decades of experience. Many had lived through false alarms, the superluminal neutrinos of the Opera experiment, later traced to a loose cable. The early claims of cold fusion, the Bike to announcement of primordial gravitational waves, later revealed to be dust. All of these had been moments when the scientific world seemed to hold its breath, only to exhale in relief when reality returned to order. This time, there was no exhale. Peer reviewers found no methodological errors. No cable had come loose. No calibration drifted. No external interference was found. The anomaly had been repeated under controlled conditions. It had been observed across independent experiments. And worse, its characteristics were too consistent to be noise, yet too impossible to be physical. A growing sense of unease permeated the scientific community. Models of reality felt suddenly narrow, fragile, like beautifully constructed illusions that could be undone by a single thread pulled from beneath. Conference calls included long, uneasy silences. Researchers double-checked their equations until sunrise, staring at them with the haunted expression of people watching logic itself begin to slip. Those who had built their careers on relativity struggled with the implications. Those who specialized in quantum foundations saw a reflection of mysteries they had long suspected, but never dared to articulate. And those who studied cosmology wondered whether they were looking at the first, observable artifact of a separate layer of reality, one hidden beneath the universe we see, like a deeper current moving beneath the visible surface of the sea. Discussions began to shift from what caused it to what does this mean? Is time foundational? Or is it emergent? Is causality absolute? Or is it a property of our particular universe, one that might be bent, bypassed, or rendered irrelevant in deeper physical regimes? Some theorists proposed early interpretations that skirted the boundaries of speculation. One idea suggested that the signal might originate from a region of SpaceTime not bound by classical ordering, a kind of boundary condition at the edge of the observable universe. Others posited that the measurement represented a form of quantum retrocausality, where information travels not backward in time, but outside of time entirely, skirting the linear structure we perceive. Another camp invoked the possibility of higher dimensional reflections, ripples from a deeper level of reality that intersect the three spatial dimensions and one temporal dimension humans occupy. If the anomaly was such an intersection, then it might represent not an object but a momentary overlap with a realm where the rules differ. Physicists debated the implications late into the night, raising questions that touched on the core architecture of existence. What if locality? The idea that objects separated in space are truly separate is an illusion. What if determinism, the belief that outcomes follow from causes, is an emergent property, not a fundamental one? What if entropy-time's arrow can bend, pause, or fracture in certain extreme conditions? These were not questions asked lightly. They formed the foundations upon which all scientific understanding rests. To question them was to question the structure of reality itself. Arguments grew heated. Some insisted that even contemplating such ideas was reckless. But data does not accommodate comfort. It demands understanding. As the weeks passed, international committees reviewed the replicability of the phenomenon. More detectors were brought into the analysis optical observatories. Deep space communication arrays, radio telescopes, cosmic microwave background monitors. The anomaly did not appear everywhere, but when it did appear, it arrived with the same impossible signature, a pulse out of order. A whisper before the universe had turned the page to the proper moment in a conference at CERN, where the anomaly's implications were being discussed with increasing urgency. One theoretical physicist presented a slide with a simple question. What if the laws we know are not laws, but shadows? The metaphor resonated through the auditorium. Perhaps the four-dimensional space-time described by relativity is not the fundamental layer of the universe, but a projection of deeper, more complex rules that sometimes reveal themselves in brief, impossible moments. A group of researchers specializing in quantum gravity proposed that the anomaly might be evidence of granularity in spacetime, tiny, discrete units of reality that blur classical temporal ordering. If the universe is woven from quantum-scale loops or units, then temporal ordering might not be continuous at the smallest scales. In rare conditions, this granularity could allow a measurement to register before the macroscopic system perceives it. Others disagreed, arguing that granularity would not produce a signal so clean, so symmetrical. A different group argued that the anomaly represented a violation of entanglement. Locality, perhaps a signal from a correlated event elsewhere in the universe, one that bypassed classical spacetime constraints. Yet even such a mechanism could not explain the pre-causal timing. Some suggested more radical possibilities. If the universe is part of a broader multiverse, then interactions between different universes might produce artifacts detectable within hours. A signal crossing from a universe with different temporal structure could appear as a pre-causal pulse. But multiverse theories, while mathematically intriguing, remain speculative and lack observational support. The debates intensified. Whiteboards filled with equations describing nonlinear time. Papers proposing new mathematical frameworks appeared overnight. Supercomputers ran simulations in clusters across Europe, Asia, and the United States. And with every iteration, the anomaly grew more undeniable. One of the most unsettling realizations came when comparing the harmonic patterns across detectors. When mapped together, they formed a structure resembling solutions to certain non-classical spacetime. Model structures that hinted at a deeper order beneath chaos. It was as if the anomaly followed rules unknown to physics. But consistent within themselves, slowly, reluctantly, the scientific community reached a point of collective recognition. The event could no longer be framed as noise. It could no longer be dismissed as equipment error. It had appeared in isolated detectors, in synchronized tests, in repeated experiments. Across continents and detection mechanisms, the phenomenon was real. Its meaning was unknown. Its implications were profound. Its violation of physics was undeniable. And so, the scientific world took a step it had not taken in decades. It admitted that something had occurred that should not have been possible. A new category of phenomenon had emerged, one not described in textbooks, not predicted by theories, not anticipated by the brightest minds. Humanity had witnessed an event that contradicted the foundations of existence and the universe. As silent as ever, offered no explanation. The chapter ends with a quiet, unsettling truth settling across the global scientific community: the anomaly is real. And if it exists, then the universe is not what humanity believed it to be. As news of the anomaly spread through the scientific world quietly, cautiously, through encrypted channels and private discussions, it became clear that curiosity alone would not be enough to confront what had emerged. Something had spoken from outside the structure of known physics. And to understand it, humanity needed to listen with unprecedented precision. Laboratories that once worked independently now aligned their instruments as if preparing a global symphony of measurement. The clocks that governed their detectors were synchronized not merely to atomic accuracy, but down to nanoseconds. Calibrated with GPS satellites, hydrogen masers, and optical lattice clocks capable of losing a single second over billions of years, for the first time in history, the world's observatories became a single instrument in the quiet control room of LIGO. The air vibrated with a tension that had nothing to do with machinery. Researchers watched their monitors as the global synchronization protocols activated. At the Virgo Observatory in Italy, technicians performed similar adjustments, aligning their detectors with timestamp signals from Europe's quantum communication satellites. At IceCube, deep beneath the Antarctic ice, engineers bathed their timing arrays in recalibration sequences. Even spaceborne detectors, NASA's Fermi Gamma Ray, Space Telescope, ESAS Gaia, and Japan's Hitomi replacement mission underwent timing harmonization, linking their internal clocks with Earth's observatories through laser, satellite channels. time itself became the tool of investigation. Once synchronization reached perfection, the search began again. Days passed in silence. Instruments listened. Data poured into servers like rainfall collecting in a vast basin. Scientists monitored every fluctuation, every spike, every ghost of an anomaly that might hint at repetition. And then, the pattern began. It was subtle at first, a faint oscillation in the LIGO data, followed minutes later by a similar disturbance in Virgo, and then by a nearly imperceptible flicker in IceCube's photomultiplier arrays. Not identical, not synchronized, but unmistakably related. Each pulse carried the same mathematical purity as the first anomalous signal, sharp, symmetrical, and unsettlingly intentional in shape. Yet each also differed, as if translated into slightly altered dialects of an unknown language. The anomaly was repeating itself, and it never repeated the same way twice. In theoretical physics, randomness is often mistaken for complexity. But this was not noise. The pulses were too structured for chance, too distinct to be artifacts, too nuanced to be mechanical interference. With each recurrence, the world's detectors recorded new variations, phase shifts, harmonic spreads, mathematical distortions, each of which seemed to obey a mysterious internal logic. The timing of the events deepened the mystery. They appeared in patterns that defied prediction, intervals that seemed almost coded, spacing that hinted at deliberation, not chaos. Some researchers wondered if the signals represented a kind of cosmic Morse coded information, structure encoded in the fabric of existence itself. Others cautioned against anthropocentric interpretation. The universe communicates in mathematics, not intention. But even mathematics can look like intention when it follows rules unknown to human understanding. As scientists probed deeper, high-energy particle experiments at CERN began to notice an unexpected phenomenon. Quantum vacuum fluctuations, those tiny, restless disturbances that flicker in and out of existence, even in perfect emptiness, began behaving oddly around the anomaly's timing. Their statistical distributions shifted, deviating from the predictions of quantum field theory. The fluctuations appeared to anticipate the anomaly. They grew slightly more ordered, slightly less random, as if influenced by something beyond the observable universe. It was as if the quantum vacuum, the foundation of everything that exists, was reacting to the anomaly before the anomaly appeared. Researchers at CERN recorded these deviations with increasing unease. Vacuum behavior is one of the most predictable features of quantum physics. The frothing sea of virtual particles that flicker through existence follows precise statistical patterns. When those patterns shift, something is wrong, not with equipment, but with the underlying reality the equipment measures. Meanwhile, space telescopes were searching the sky for any corresponding astronomical events. The James Webb Space Telescope, with its infrared sensitivity, scanned deep fields of ancient light regions older than galaxies, older than stars, regions bathed in the faint afterglow of the early universe. Webb's detectors noticed subtle distortions in certain deep space regions, distortions that matched the anomaly's timing with uncanny accuracy. They were not gravitational lensing events, not star formations, not interactions of dust clouds or cosmic radiation. They were faint, smooth distortions in the structure of SpaceTime's distant fabric ripples that did not behave like gravitational waves. Light passing through these regions bent in ways that did not match Einstein's curvature equations. The distortions were too orderly, too non-chaotic, too symmetrical. Astronomers compared these distortions to theoretical models. None of them matched. The distortions did not correspond to mass. They did not correspond to energy. They did not correspond to anything that should cause space-time to bend. It was as though the universe's geometry had momentarily shifted, subtly reconfiguring in response to something beyond it. As data accumulated, a picture began to formulate of an object, not of a particle, but of a deformation. The anomaly did not behave like a thing. It behaved like a modification in the structure of reality itself, a temporary reconfiguration of laws, that were previously assumed to be immutable. At MIT, theoretical physicists plotted the anomaly signals against the distortions observed by space telescopes. When the graphs were overlaid, an astonishing correlation appeared. The timing of the pulses matched the onset of the distortions. The shapes of the pulses mirrored the curvature deviations observed in distant regions of the cosmos. Even the harmonic variations seen in the detectors had analogs in the distortions. Geometric patterns. It was as if the anomaly and the distortions were part of the same phenomenon, one detected on Earth, the other written into the sky. A deeper mystery emerged when multiple layers of data were combined. Gravitational wave readings, quantum phase measurements, entropy gradients, and light curve deviations all displayed faint, synchronized behaviors. Not synchronized in time, but synchronized in structure, as though they were different shadows cast by the same invisible object moving behind an opaque curtain. Some of the brightest mathematical physicists began arguing that the anomalies pointed to a deformation not in spacetime, but in the underlying rules from which spacetime emerges. Quantum gravity models often propose that spacetime is not fundamental, that it arises from entanglement, patterns, or information networks at deeper levels. In these models, the geometry of the universe is not a stage, but a consequence. If this is true, then the anomaly may be a momentary shift in the deeper informational substrate and event, not in spacetime, but beneath it. One theoretical paper suggested that the anomaly could represent a boundary condition, breach a moment when the universe's deeper structure became visible within the emergent fabric of spacetime. Another proposed that the anomaly reflected interference between multiple layers of physical law, similar to the way interference patterns appear when overlapping waves of different frequencies cross paths. Even more radical interpretations emerged. Some mathematicians proposed that the anomaly might originate from a region where the universe transitions between different vacuum states, an echo of the early cosmos still reverberating through its structure. Others speculated that it could be evidence of an additional temporal dimension, one orthogonal to the familiar flow of time, through which information could move without violating causality in a higher dimensional sense. As theories blossomed, simulations were run on the world's most powerful supercomputers. Blue Gene Summit Fugaku, Aurora machines capable of trillions of calculations per second, were tasked with modeling the anomaly. They were fed the timing data, the waveform shapes, the quantum shifts, the astronomical distortions. But every simulation ended the same way. The models broke, not computationally. Conceptually, no equations set. No quantum framework, no relativistic structure, no multidimensional geometry could generate a phenomenon that behaved like the anomaly. Every attempt to reproduce it mathematically ended in contradiction. Simulations produced infinities, undefined values, recursive loops, or structural failures. It was as if the anomaly existed in a region of physics whose rules had not yet been written. One physicist described the failure as watching mathematics recoil. Equations that normally behave predictably twisted themselves into impossible forms, collapsing as if the underlying assumptions were inadequate. Others said the simulations behaved like dreams, structured at first, then breaking apart under scrutiny. With each failed model, the mystery deepened. The anomaly refused categorization, refused replication within known frameworks, refused containment within any equation that described the universe humans believe they occupy. This led several theorists to propose an extraordinary idea. Perhaps the anomaly does not obey the same laws as everything else. Perhaps the laws of physics humans know are approximations, useful tools, but not fundamental truths. Perhaps reality is layered and the anomaly is a glimpse of a layer beneath. The possibility was unsettling. If the anomaly represented a deeper level of physical law, then the universe humans observe might be like a shadow, cast upon a wall, stable only because deeper processes maintain its coherence. A single disturbance in the deeper structure could echo into the emergent reality, creating effects that appear impossible within the rules of the emergent world. As the investigation continued, The behavior of entropy, the measure of disorder, drew particular attention. In regions where the anomalies' astronomical distortions appeared, entropy dipped slightly, not reversed, not violated, but dipped. This was unprecedented. Entropy is famously monotonic. It increases. Yet these dips, tiny though they were, suggested moments of unusual order within the cosmos, as if the underlying reality had tightened, briefly pulling the visible universe into a more structured state. The anomaly seemed to impose order rather than chaos. This was profoundly troubling. Chaos is natural. Order is imposed. Some began to wonder whether the anomaly might be a kind of organizing event, an imprint of a structure attempting to manifest within our universe. But what could impose such order? Not gravity, not electromagnetism, not the strong or weak nuclear forces. These forces shape matter. They do not rewrite the rules. Through weeks of data collection, one truth emerged more clearly than any other. The anomaly was not an object. It was not a signal. It was not a particle, a wave, or a physical event. It was a deformation in the structure of reality, a momentary reconfiguration of the rules, a shift in the order that defines existence. The implications were staggering. Every physical theory built over 500 years assumes the rules are stable. But what if they are not? What if the laws of physics are not the pillars of reality, but the surface patterns of something deeper, something capable of movement, change, or expression? By the end of the deeper investigation phase, the global scientific community had reached another unsettling conclusion. The anomaly could not be modeled because it did not belong to the deep a layer of physics that humans understand. It belonged to the layer that makes physics possible, and that layer had stirred in the weeks that followed the deeper investigation. The anomaly began to change. What was once a faint whisper at the edges of detection grew into a phenomenon that refused to remain confined to the instruments that first observed it. Subtle, elusive, and unnervingly consistent. It began to appear in different regions of the cosmos, manifesting in forms so varied and yet so unmistakably connected that no scientist could interpret them as coincidence. One night, as the world slept beneath a turning sky, the James Webb Space Telescope recorded a sudden distortion in a region of ancient starlight known for its silence. Webb's sensors captured a subtle shift to curvature of space-time that did not match any gravitational lensing profile. It appeared without mass, without energy, without any visible cause. Minutes later, the Atacama Large Millimeter Array in Chile detected a faint, regular warping in the microwave background radiation. And across the globe, several synchronized optical surveys recorded brief deviations in distant quasars' light curves, as if some unseen force had pressed momentarily against the fabric of the universe. These events were separated by millions of light-years in space, and mere minutes in time. They had no shared astrophysical source, no supernova, no gamma-ray burst, no collision of cosmic giants. Yet their signatures, when processed, carried the same strange mathematical structure that the anomaly had shown on Earth. The same symmetry, the same pattern of impossible timing, the same refusal to obey the rules that bind all things it was spreading. And as it spread, its defiance grew clearer. Relativity, Einstein's great architecture of space and time, became the first pillar to tremble. Space-time curvature responded to mass and energy in predictable ways. But these new distortions followed no such logic. They bent light in patterns no mass distribution could explain. They arrived without the propagation delay expected from gravitational influences. They seemed to manifest instantaneously in multiple locations at once, as if circumventing the cosmic speed limit. But relativity was not the only structure under threat. Quantum field theory, the framework that governs the dance of particles and fields, suffered similar violations. In several high-energy laboratories, physicists noticed that the anomaly seemed to ripple through the quantum vacuum itself. Whenever the anomaly appeared in the sky, synchronized detectors registered slight deviations in the energy density of vacuum fluctuations. Virtual particles flickered differently, as though their probabilistic existence were being nudged by something outside the quantum fields they inhabit. Even the behavior of entanglement correlations shifted subtly, as if the delicate web of interconnected quantum states had been momentarily rewoven. The anomaly was touching every layer of the universe spacetime. Quantum fields, information structures with an ease that suggested it did not belong to any one layer. It interacted with reality as if reality were merely one possible configuration of something deeper. Most unsettling of all was the growing suspicion that the anomaly somehow responded to observation. Not directly, not as a conscious entity might, but in a manner that echoed the strange, observer-dependent behavior of quantum mechanics. When the anomaly was monitored with greater sensitivity, its manifestations grew cleaner, more defined as though sharpening under scrutiny. Yet paradoxically, timing analyses showed that the anomaly signals almost always occurred. Microseconds before the observational windows officially opened, it behaved like something that anticipated measurement in a sense. It behaved like something that existed outside the linear boundary of awareness, as if measurement did not reveal it, but allowed it to overlap with the measurable world. The notion that awareness and appearance might be entangled in this way unsettled even those who had dedicated their careers to the philosophical puzzles of quantum interpretation. Then came the discovery that pushed the scientific community from unease into something closer to dread. When astrophysicists compared all recorded anomalies against cosmological data, they found something startling. A faint echo of the same mathematical structure, the same harmonic relationship between phase and symmetry could be traced in relic radiation from the early universe, not in the cosmic microwave background as measured today, but in the statistical imprints from its earliest models. The anomaly structure existed in data extrapolated to epochs older than the first stars, in patterns older than atoms, in distributions formed less than a trillionth of a second after the Big Bang. It was as if the anomaly had always been here, as if it were woven into the universe's birth. The implications were enormous. If the anomaly's signature existed in primordial radiation, then it might predate the universe itself. It might not be an event at all, but a residue and artifact from whatever reality existed before spacetime inflated into being. Something older than the Big Bang, something from a boundary condition at the edge of existence. Cosmologists began to speculate cautiously that the anomaly might represent information leaking from a deeper stratum of reality, from a domain beyond spacetime's beginning, or from another universe connected to ours through a structure unrecognized by current models. Other theorists ventured into even stranger territory. Perhaps the anomaly did not originate from before the universe, but from outside it. If spacetime is like a bubble, the anomaly could be a ripple passing through the membrane from an adjoining realm. Or perhaps the universe is emerged of vast computation. Unfolding from deeper informational rules in the anomaly is a momentary glimpse of the underlying engine. This possibility transforms scientific curiosity into something more primal. Because if the universe is emergent, if the laws of physics are not fundamental, but derived, then the anomaly could represent a moment when those laws falter. A flicker of instability in the deeper framework. A crack forming in the foundation of reality's architecture. Researchers specialized in simulations and computational physics noted a troubling detail. The anomaly's behavior resembled the glitches seen in complex simulations, when underlying processes struggled to reconcile conflicting conditions. A moment of tension between code and output. A fault in the generative structure. The idea was not that the universe is a literal digital simulation, but that it may function like one where emergent laws arise from deeper rules, and those rules may not be perfectly stable across scales. The possibility brought with it a new question. One whispered in late-night meetings and typed reluctantly into research notes. What if the anomaly is growing? Data showed that its manifestations were becoming more frequent, more intense, and more deeply embedded in cosmic structures. Astronomical distortions increased in magnitude. Quantum deviations grew sharper. Signatures multiplied across different detection methods. At first, the anomaly had been a whisper, a single, impossible event. Now, it was a murmuring chorus, faint but unmistakably rising. If the anomaly was intensifying, then the deeper framework beneath reality might be shifting slowly, subtly but undeniably. For some researchers, this possibility felt like standing on a frozen lake and hearing the cracks forming beneath the ice. The universe is vast, ancient, and resilient. But if its laws are emergent, then they may not be permanent. They may be maintained by deeper processes that can wobble, fracture, or reset. Physicists began working with a new vocabulary, one that felt uncomfortably theological despite its scientific grounding. They spoke of the substrate, the foundation layer, the protostructure of reality, the deep law. Terms that implied a hierarchy beneath physics, a realm where the mechanisms that generate space-time reside. It was within this context that the true fear emerged. If the anomaly was a deformation of the deeper layer, if it represented instability, then the consequences could be profound. Not merely a challenge to current models, but a threat to the continuity of the universe itself. Because emergent systems collapse when their foundations falter. Nature does not preserve illusions when the rules change. Every day more data arrived. Every day the anomaly appeared somewhere new. And every day the questions deepened, darkened, and multiplied across the scientific world. A quiet dread settled, a dread contained. Not in words, but in the stillness of researchers staring at screens long after midnight. The anomaly was no longer a curiosity. It was no longer a measurement problem or a theoretical puzzle. It was a sign that reality itself might not be stable, a sign that the universe may be revealing its hidden layers, a sign that something deeper is unfolding. And for the first time since humanity began studying the cosmos, scientists wondered whether they were witnessing not just a discovery, but the first observable crack in the cosmic foundation. As the anomaly grew in scale, in presence, and in defiance, the scientific world reached a threshold where observation alone was no longer enough. What had begun as a whisper beneath the noise of instruments had become a challenge thrown at the entire architecture of physics. And when a phenomenon refuses to obey the laws of nature, theories rise to confront it. They form like constellations around an unfamiliar star, each one an attempt to understand what lies at the center of the impossible in universities, research institutes, and quiet offices lit by the glow of midnight screens. Theorists began weaving explanations. Some were expansions of long-standing frameworks. Others were radical departures, ideas whispered at the edges of scientific imagination. All were born from the same realization: the anomaly did not fit within the existing structure of reality. And so, perhaps, the structure itself needed to be expanded. The first family of theories came from quantum. Gravity, the long-sought unification of Einstein's smooth spacetime, and the restless, granular world of quantum mechanics. In these models, reality is not a continuous stage, but a lattice, a shimmering grid of tiny, indivisible units known as Planck-scale structures. At scales far below atoms, space and time lose their familiar forms. They dissolve into loops, spin networks, or discrete informational nodes. To those who study quantum gravity, the anomaly was not merely a disturbance. It was a revelation. Its peculiar timing, its clean symmetry, its refusal to abide by classical causality. All of these suggested that the event might originate from the granular understructure of reality. If spacetime is built from tiny quantum units, then the anomaly might be a moment when the deeper lattice revealed itself, a tremor in the foundation stones upon which the universe is constructed. But even this elegant explanation faltered. Granular spacetime should introduce noise at microscopic scales, randomness born of quantum discreteness. Yet the anomaly carried precision, order, structure. It behaved less like a flicker of fundamental granularity and more like a deliberate pattern. The lattice theory offered insight, but not closure. A second possibility drew attention from cosmologists and string theorists alike: multiverse leakage. In this interpretation, our universe is not alone. It floats within a vast sea of other universes, its own laws, dimensions, and histories. Normally, these universes remain isolated, sealed by the very geometry of higher dimensional space. But under rare conditions, information might bleed from one universe into another, like a whisper passing between adjoining rooms separated by an unseen wall. The anomaly's pre-causal timing, its ability to appear simultaneously across different cosmic regions, and its refusal to behave like any known particle or force-all hinted that it might not belong to this universe at all. It may be a visitor from elsewhere, arriving through pathways that do not exist in the four-dimensional space-time humans inhabit. Some researchers imagined the anomaly as the shadow of a higher dimensional event, a projection from a realm where time flows differently or not at all. Others pictured it as a collision between cosmic membranes, a momentary overlap between universes that leaves a trace in the physics of both. But even here, the theory struggled. The anomaly did not appear random or chaotic as one might expect from inter-universal interference. Instead, it seemed governed by rules unfamiliar yet internally consistent. The multiverse hypothesis explained the origin, but not the behavior. The third theory emerged from the world of quantum information, where the boundaries of space and distance are more philosophical than physical. Known as non-locality collapse, this idea treats the universe as a single, interconnected whole. In this framework, separation is an illusion. Every particle, every point in space, every moment of time is woven into a network of correlations that transcends location. Two proponents of this view, the anomaly's ability to manifest in multiple places at once, was not surprising, which characteristic of a reality built on connection rather than separation. If the universe is fundamentally non-local, then an event in one region can influence distant regions without traversing the space between. But the anomaly was not merely, it appeared before measurement sequences, implying a collapse not only in distance, but in temporal ordering. This forced theorists to confront a more unsettling possibility. What if time itself is non-local? What if the past, present, and future are woven together in a structure that does not respect linear flow? In such a universe, the anomaly might be a signal not from elsewhere, but from elsewhere. Yet this theory, too, met resistance. Non-locality explains correlation, not causeless emergence. It offers connection, not creation. Another model arose from the depths of cosmology, false vacuum instability. According to quantum field theory, the universe may not be in its lowest possible energy state. It might exist in a metastable condition, a temporary calm that could collapse into a more fundamental vacuum. If such a collapse began in a distant region of the universe, the boundary of the new vacuum would expand outward at nearly the speed of light, rewriting the laws of physics in its wake. Some cosmologists suggested that the anomaly might be an early tremor of such a transition, a shift in the vacuum state of reality itself, a sign that the universe is preparing to reorganize at the deepest possible level. But this theory carried existential implications. A true vacuum transition would be catastrophic, obliterating everything in its path. Yet the anomaly did not bring destruction. It brought structure. It brought patterns. It brought messages written in the language of impossibility. False vacuum instability offered terror, not clarity. One of the most philosophically profound theories was the causal loop model. In this framework, time is not a straight line, but a self-referencing structure. Events can influence earlier events. Effects can contribute to their own causes. Time becomes circular, recursive, layered upon itself. The anomaly's pre-causal behavior fit neatly within this idea. If time loops, then an event might appear before its trigger, because the trigger may lie in its future. Physicists who favored this view saw the anomaly not as a break in causality, but as evidence that the universe does not obey simple temporal flow. Instead, reality might operate as a network of interdependent moments, where past and future are co-authored by one another. But even here, contradictions lurked. A causal loop must stabilize into consistency. Yet the anomaly introduced fluctuation signals that were similar, yet never identical. It behaved like something exploring possibility space rather than reinforcing. Closed loop. Then there was the holographic principle, a theory born from black hole physics, where information is stored on surfaces rather than in volumes. According to this idea, the three-dimensional universe humans experience may be a projection from a deeper, two-dimensional, informational boundary. Reality is a hologram. Physics as encoded data. Existence as a shadow cast by a more fundamental structure to those who embraced this vision. The anomaly was a glitch, not in the universe, but in its projection. A moment when the underlying code revealed itself. A ripple in the informational boundary manifesting as a distortion in emergent spacetime. The precision of the anomaly's waveform. The mathematical symmetry of its harmonic patterns. And its ability to influence quantum vacuum behavior all hinted at a deeper informational substrate. But the holographic model, as powerful as it was, stumbled on one detail. Holograms are stable. Errors in the boundary code should produce systematic distortions, not irregular, evolving signatures. The anomaly did not behave like a glitch. It behaved like a message. Finally, the most radical and yet most comprehensive framework emerged: emergent spacetime theory. In this interpretation, spacetime is not fundamental. It arises from entanglement patterns, informational structures, or quantum computational processes occurring in a deeper, hidden layer of reality. The universe becomes not a stage, but a product of phenomenon generated by interactions in a realm beyond comprehension. If spacetime is emergent, then the anomaly may represent a failure or shift in the generative system, a moment when the deeper processes that create space, time, and physical law revealed their presence. The anomaly's ability to synchronously distort cosmic regions, influence quantum fields, and defy causality all pointed to a reality where spacetime itself is secondary. What humans perceive as physics might be like the surface of water, beautiful, coherent, yet shallow compared to the deep currents beneath. Emergent spacetime theory explained more than any other model. It accounted for the anomaly's layered influence, its independence from physical laws, its ability to predetermine observation, its mathematical symmetry. But even emergent spacetime faltered, for the anomaly did not behave like a failure. It behaved like an expression. It was structured. It was ordered. It was meaningful. And so, no theory, no matter how bold, could fully contain it. Quantum gravity offered granularity, but not intelligence. Multiverse leakage offered origin, but not coherence. Non-locality collapse offered connection, but not creation. False vacuum instability offered transformation, but not structure. Causal loop theory offered time flexibility, but not evolution. Holography offered encoding, but not dynamism. Emergent spacetime offered depth, but not intention. Every theory illuminated a part of the anomaly, but none illuminated the whole. Instead, the anomaly sat at the intersection of all frameworks, like a doorway leading into regions of reality where known theories dissolve into shadows. The scientific world stared at this doorway, knowing it opened onto a landscape no one had mapped, and the anomaly, steady and silent, waited. It offered no explanation, no simplification, no surrender to human understanding. It simply existed, calm and indifferent, as if inviting the universe to reconsider itself in the end. One conclusion rose above all others: quiet, unsettling, undeniable. The anomaly was not merely a break in known physics. It was a sign that the laws humanity follows are not the laws that govern reality. And whatever lies beneath those laws has begun to reveal itself as the anomaly deepened, and the theories around it grew more elaborate. The scientific world entered a new phase, one defined not by speculation, but by a global mobilization unlike anything in the history of physics. A mystery had appeared that refused to answer to existing tools, existing models, or the comfortable assumptions that had guided science for a century. And so humanity began building a new arsenal to confront a ton array of instruments, collaborations and experiments designed not simply to observe the universe, but to interrogate it. The effort began with telescopes already pointed toward the sky, The James Webb Space Telescope, drifting silently at the L2 Lagrange point, shifted its gaze to regions where space-time distortions had been recorded. JWST's infrared detectors, capable of peering through cosmic dust to observe light older than stars themselves, searched for faint ripples in ancient starlight. Webb found them delicate bends in the geometry of distant galaxies, distortions with no gravitational origin, patterns that flickered with the same quiet cadence as the anomalies' terrestrial signatures on Earth. LIGO continued to operate with unprecedented precision. Its vacuum arms, stretching across kilometers of American soil, became listening posts for whispers from the depths of space-time. Engineers refined the laser interferometers, reducing noise, stabilizing mirrors, and using machine learning systems to isolate faint disturbances buried beneath the Earth's vibrations. Virgo, CAGRA, and LIGO India joined the effort, forming a network of gravitational interrogation stations across the planet. Together, they synchronized their clocks down to billionths of a second. They watched for pulses that did not belong to collapsing stars or merging black holes, and they found them regular, symmetrical, defiant of traditional waveforms. Then came the square-kilometer array still under construction. Yet already contributing through its prototype networks in South Africa and Australia, SKA, designed to be the most sensitive radio observatory ever built, would eventually hear the faintest murmurs of the universe. Early arrays detected subtle modulations in cosmic radio emissions, fluctuations that matched the anomaly's expanding footprint. These variations appeared not as noise, but as fingerprints of an unseen force shaping radio waves from across the cosmos. China's FAST telescope, the world's largest single-dish radio observatory, recorded similar disturbances. Its massive dish, cradled in a natural valley, detected unusual coherence patterns in fast radio bursts, mysterious explosions of radio energy that normally behave with chaotic unpredictability. Some bursts now carried hints of structure, faint repetitions that mirrored the anomaly's timing sequences. FAST's engineers combed through the data with growing astonishment. The patterns were too subtle to be natural, too complex to be random. Meanwhile, CERN prepared for a new frontier in particle physics. The Large Hadron Collider underwent a series of upgrades to increase luminosity, refine beam stability, and enhance detector sensitivity. Though built to explore the subatomic world, CERN's detectors began searching for vacuum anomalous shifts in zero-point energy that mirrored fluctuations observed during the anomaly's cosmic events. Some experiments produced results that defied expectation. Vacuum energy densities oscillated in patterns unrelated to particle collisions, as though the quantum vacuum itself were participating in the same strange dance observed in deep space. As instruments grew more advanced, so too did the collaborations behind them. For the first time, astrophysicists worked directly alongside quantum information theorists, mathematicians, computer scientists, and philosophers. International task? Forces formed groups dedicated not to defending existing theories, but to exploring the boundaries of understanding. These teams gathered in conference rooms, virtual meeting spaces, and high-altitude observatories, their conversations weaving together threads from every field. What is a law of nature? What is space? What is time? What happens when the universe itself becomes a variable? Physicists who once spoke only in equations began integrating ideas from quantum logic, category theory, and metaphysics. Mathematicians who specialized in topological spaces now collaborated with astronomers studying the large-scale structure of the cosmos. Philosophers schooled in the nature of causation found themselves discussing entanglement, emergence, and the ontology of information. The anomaly demanded interdisciplinarity. It would not be solved by any single branch of knowledge, because it did not belong to any single layer of reality. New detectors soon joined the effort machines built, specifically to capture the anomaly with higher resolution. Some were upgrades to existing observatories. Others were entirely new devices, designed to sense distortions in quantum fields, fluctuations in gravitational curvature, or perturbations in informational structures. One such detector built in Japan was engineered to observe decoherence patterns in large entangled systems. Another, developed by a European consortium, used superconducting qubits cooled too near absolute zero to amplify tiny fluctuations in the vacuum state. These detectors were not looking for particles or waves. They were searching for shifts in the underlying rules that govern them. A ripple not in spacetime, but in the mechanism that creates spacetime, alongside hardware. Advanced algorithms emerged, deep learning systems trained on vast data sets of cosmic events, quantum interactions, and anomaly signatures. These algorithms began searching for hidden patterns in the anomaly's behavior. They examined its timing, its frequency structure, its geometric symmetries. Some algorithms detected correlations between the anomaly and regions of the sky where dark matter density was unusually high. Others found faint periodicity tinting, that the anomaly may not be random at all, but cyclical, a pulse in the universe's deeper machinery. One algorithm, built by a team in Germany, identified a pattern so unusual that its creators hesitated to publish it. The anomaly's variations resembled the output of a complex computational system, something akin to a recursive function, where each event built upon previous events in a structure that seemed both adaptive and self-referential. It echoed the architecture of emergent systems rather than the randomness of natural noise. If accurate, this would imply that the anomaly was not merely a deformation, it was an evolving process. As instruments grew more sophisticated, so did humanity's ambitions for future missions. Plans emerged for quantum satellites, capable of detecting pre-causal fluctuations in the fabric of space-time devices that would orbit Earth and synchronize constellations. It's capable of triangulating anomaly signatures with greater precision. There were proposals to place detectors at Lagrange points, where gravitational forces balance and allow instruments to float in stable positions, ideal for long-term observation. These spaceborne observatories would be shielded from terrestrial noise, offering a clearer window into the cosmos. Researchers also proposed missions that reached far beyond Earth. Some envisioned sending quantum sensors into deep space devices, designed to drift through regions where cosmic distortions had been observed. These probes would not look for planets or stars. They would search for the boundary conditions of reality itself, exploring places where the anomaly's presence seemed to ripple across the galactic structure. A bold idea emerged from a collaboration between NASA, ESA, and Japanese researchers: the creation of artificial quantum vacua in controlled environments, using intense magnetic fields and ultra-low temperatures to manipulate the zero-point energy state by crafting perfect vacuums in which no known particles could interfere. Scientists hoped to provoke interactions with the anomaly, at least understand how it affected the very emptiness upon which the universe is built. The theoretical risks were significant. A shift in the vacuum state could rewrite physical law, even in small regions. Yet the anomaly already hinted that the vacuum was not as stable as once believed. If reality was undergoing a deeper transformation, understanding that transformation became essential not merely for science but for existence. Despite the monumental scale of these efforts, progress was slow. Instruments captured more data, but no instrument alone could describe the anomaly. It transcended detection methods, manifesting in gravitational sensors, quantum measurements, radio observations, and cosmic imaging. It behaved like a unifying phenomenon, something that existed across every layer of the universe at once. Touching structures from the cosmic web to the smallest fluctuations of the vacuum, scientists confronted a possibility that blurred the line between physics and philosophy. The anomaly might not belong to the observable universe at all. It might be the shadow of a deeper order revealing itself through distortions in the emergent world. This shift in perspective reshaped the scientific community's understanding of what they were studying. They were not observing an object. They were not observing a force. They were not observing a particle, a field, or even a wave. They were observing a deviation in the rules that generate such things, and so their final task was not to describe the anomaly within physics, but to ask what happens when physics itself becomes the subject of investigation. This recognition led to a phrase that began circulating in research documents and conference halls, a phrase spoken with the solemnity of an ancient truth rediscovered. We are investigating something older than physics. It was not metaphor. It was acknowledgement. The anomaly did not break the laws of nature. It hinted that the laws themselves are emergent, temporary, perhaps even fragile. And for the first time, humanity stood before a mystery that reached into the foundations beneath. Existent since is a deep architecture from which reality arises. No longer was the anomaly merely a measurement. No longer was it a mystery to solve. It was a question directed at the universe itself. What lies beneath everything? And the universe in its silence seemed to say, look deeper, across the vast landscape of scientific inquiry where equations stand like monuments and theories unfold like constellations. There comes a moment when the pursuit of knowledge reaches the boundary of the measurable. Beyond that boundary, the universe no longer behaves like a system of rules waiting to be deciphered, but like a presence. It's quiet and inscrutable, offering not answers but reflections. And as humanity stands before the anomaly, that presence feels closer than ever. For centuries, the idea of reality had been a comfort, constant, something that could be touched, measured, predicted. Space was the stage, time the script, matter the actors. Everything played its part with beautiful obedience. But now, with the anomaly appearing like a fracture in the cosmic mirror, the question arises, what if the stage is not real? What if the script is incomplete? What if reality itself is not fundamental, but something woven, something emerging from deeper? Principles that remain hidden beneath the surface. Physicists, philosophers, and mathematicians begin to confront the same ancient unease. If reality is emergent, then what lies beneath it? If space-time is not the foundation, then what foundation permits it? The universe is a structure. Who or what constructed it? These questions, once dismissed as metaphysical luxuries, now sit at the center of scientific discourse. The anomaly, with its defiance of causality and its quiet rewriting of the known, forces the scientific community to rethink not just the laws of physics, but the nature of existence in the silence of observatories where scientists watch data. Streams ripple across their screens like cosmic messages. A new humility emerges. Humanity, once confident in its models of the universe, must now face the possibility that the universe is far stranger than expected. That the familiar laws governing planets, particles, and forces are not eternal truths, but temporary expressions of something deeper. The idea unsettles and expands the mind simultaneously. If reality is emergent, then the universe may not be a physical object at all, but a process in unfolding, a computation, a dream of structure floating atop a sea of deeper order. In that deeper order, the anomaly appears like a ripple, a disturbance that briefly reveals what lies beneath. What does it mean to exist in a universe that is not fundamental? What does it mean to be creatures who evolved inside a set of laws that may themselves be impermanent? If the ground beneath reality can shift, then so too can the meanings of truth, stability, and understanding. For some, this realization is terrifying, the unraveling of a worldview. For others, it is liberating, the invitation to explore realms not yet imagined. But for all, it is profound. Because if the anomaly is real, then humanity's understanding of its place in the cosmos must change. Consider the possibility that consciousness is not separate from the universe, but part of the same emergent structure. That the mind and the cosmos are built from similar principles, information, pattern, interaction. If the anomaly anticipates observation, if it sharpens under scrutiny, then perhaps reality is not indifferent to awareness. Perhaps the observer is woven into the fabric of the observed. This is not the naive claim that mind creates reality. Rather, it is the sober recognition that the act of observing may be entwined with the deeper rules from which reality emerges. That consciousness, far from being an accidental byproduct of biology, may be a natural expression of the universe's underlying architecture. If so, then humans are not mere spectators. They are participants, small, fragile, transient, but participants nonetheless in the great unfolding of existence. It raises another question. Whispered by thinkers across time, are humans interruptions in a larger cosmic pattern, or are they reflections of it? The anomaly, with its impossible behavior and its refusal to be contained by known physics, forces a reconsideration of the human role. Not as rulers of the universe, nor as insignificant dust, but as beings capable of perceiving the universe perceiving itself. A species that, through instruments and inquiry, allows the cosmos to become aware of the structures from which it arises. In this way, consciousness becomes not an evolutionary accident, but a cosmic function, a window through which reality examines its own foundations. The anomaly, instead of being an external disturbance, becomes part of that examination. A reminder that the universe is not a static object, but a dynamic, evolving entity, still revealing its own nature. And then another question arises, quiet but irresistible. If the universe allows the impossible, what else might it allow? If a signal can appear before causality permits it, SpaceTime can bend without mass, quantum fields can shift in anticipation of events, the laws of physics can tremble like a curtain in a breeze. What other phenomena lie beyond the horizon of understanding? What deeper patterns wait in silence, ready to emerge when humanity's tools and theories expand enough to perceive them? It's the idea that the universe may be more flexible, more dynamic, more alive than previously believed, reshapes everything from cosmology to philosophy, from quantum theory to metaphysics. The cosmos no longer appears as a cold, indifferent expanse of matter and void. Instead, it resembles an intricate tapestry woven from rules that shimmer and bend, always revealing new depths to those brave enough to seek them. As scientists ponder these implications, they realize that the anomaly is not simply a challenge. It is an invitation, a call to step beyond the edges of known physics, to explore not just the universe that is visible, but the universe that is possible. In long conversations held beside chalkboards filled with equations, in quiet offices where researchers stare into the dark between stars, in observatories perched on mountains above the clouds, a new science begins to form, one that blends the rigor of mathematics with the wonder of philosophy, one that accepts uncertainty not as failure but as the doorway to discovery. And as the anomaly continues to whisper through detectors, humanity begins to sense the magnitude of what it has encountered. If reality is not what it seems, then perhaps existence is larger than the universe. If the universe is emergent, then perhaps it has origins not in matter, but in principles yet unnamed. If time is not linear, then perhaps the future is already entangled with the past in ways that transcend comprehension. If consciousness is part of the cosmic structure, then perhaps awareness itself is a force woven into the architecture of reality. Each possibility opens not just a new question, but an entire landscape of inquiry. The universe becomes a place not of limits, but of layers, not of constraints, but of revelations. And at the heart of it all lies a simple, humbling truth. Humanity has barely begun to understand where it lives. As the chapter draws to its close, the camera of the imagination drifts outward from laboratories glowing in the darkness, to observatories listening to the quiet hum of the cosmos, to the swirling galaxies that dance across the night sky. From star nurseries blazing with color, to the cold silence between clusters, to the filaments of dark matter stretching like invisible threads through the universe. Through all of this, one realization echoes. Reality may not be what humans once believed. It may not be fixed, it may not be singular, it may not even be complete, but it may be far more beautiful, intricate, and conscious than ever imagined. And the anomaly, silent, elegant, impossible, remains as the first doorway into that deeper truth. As the universe expands in all directions, humanity stands at the edge of a vast, uncharted frontier. A frontier not of galaxies or stars, but of understanding. A frontier where physics blends with philosophy, where questions become guides, and where the next great discoveries will not simply reveal more about the cosmos, but more about existence itself. The film ends, not with certainty, but with awe. The music softens, the imagery fades, and a final thought lingers like a whisper from the depths of reality. Reality may not be what we think, but it may be far more wondrous than we have ever dared to believe.